to know what exactly I'm going to talk about. Just maybe get into these questions. I mean, I'm still thinking about the coulomb atom, the confined atom, and the Higgs atom. Coulomb atom, you're talking about waves, frequency, um, light, like a lot of just diffraction, um, photons going into other photons, and not photons going into other. I shouldn't say that. Not photons going into other photons. Just uh, photons being physically attracted or magnetically attracted to other properties or states or other static states of matter. So um, maybe it's not helpful. I mean, what do you call that? You call that momentum? Does it matter if you call it momentum or if you call it bits gravitating towards other bits? I don't really know. I don't really know why it matters. Really, um, why there's a difference, why there needs to be a difference, or why there doesn't need to be a difference, or if we're just playing like teams or sides. Like with Newton, you're just saying, well, you can't gauge anything anyway. It's still going to be like a stretch of gravity, like a um, Einstein mechanic. Um, so if you're playing momentum, essentially in the curvature of photons, yeah, you're taking into consideration, I guess, cold fusion and decay, because you know, and then that's the interconnectedness between space and light, or however you see it, and yeah, so you just um, try. There's no sense in, I guess, having the obligation to call it the like giving it this momentum feature if you're just not going to go all the way with it and say it's just momentum and that's what it's doing. That's what it's wrapping around. That's how it's wrapping around. Um, there is no. I mean, essentially, there would be no connective force like that, though, right? There wouldn't be a connective momentum like that. So the connective momentum would really have to be just uh, longitudinal force, like longitudinal photons that are making a pattern. So we're not talking about a magnetic frequency. Um, you can't really say that it's any different. If you want to use Thomas Young's waves, you really have to use diffraction, and that doesn't make any particular sense. If you get down to it, if you really try to understand it for what it is, it just doesn't make any sense that uh, in the slit there's not going to be actual diffraction. So um, yeah, or why can't you even think of it that way? Since it's going to be, I mean, it doesn't have any. I don't know. It just doesn't have any uh, gravity. No, I mean, it doesn't have any meaning. And well, I lost my train of thought there, but yeah, I mean, it's not going to have any strength theoretically. It only seems to work mathematically, which a lot of these things do, especially such as bent space, not bent space, or relativity. I I mean, at the infinite level. relativity does not seem to work at the infinite level, which it doesn't. So it just seems uh, like they are giving it. I mean, if they're like, in particular with the Einstein rings, if they're talking about the sun in its superposition and the Earth in its superposition, and uh, they're talking about a ring uh, seen from far away in space. I mean, do you decide that the ring is outside of space? I mean, is an Einstein ring something that you see in the sky? Do you see the moon when it's closer to you in a telescope, or do you see it further away? That sort of thing. I mean, does the apple fall from the tree to the ground, or does it fall? I mean, does it fall from the tree to the ground? So these particular problems, like especially with the Minkowski, which is I think pre-Dirac, or sorry, pre-general wave function, relativistic wave function. It's just such an easy way to come up with anything. I guess even in the magnetic force, like saying there's four 360-degree angles. Um, so that's not really the best. It's not really the best case scenario. I did bring up hourglasses, but I knew that hourglasses weren't going to work in a anti-gravity. They don't. Nothing works in an anti-gravity um, sort of sense. So I'd say there's a real problem there. Um, would I have a problem just because uh, the car is moving faster? That the car is moving faster, or there's more thermo direction happening in the car, and that means that there's a higher momentum. So the momentum is accelerated. I mean, it doesn't seem to really. Sorry, the energy is accelerated. So the acceleration causes the, a bigger momentum. I mean, that's sort of what my difficulty is with these sort of things. I mean, it doesn't seem to be they don't seem to be totally interchangeable. I mean, if you increase the engine, or you use more gas, then the momentum would you would have more momentum. So yeah, I mean, you could say that you have there's a higher momentum in the current anyway. So yeah, it just sort of is a little bit. It's just sort of a little bit unfortunate. I mean, the Einstein ring one was really big for me because I mean, people see the ring around the moon all the time. They see the ring around the sun. I'm sure enough. Not everybody's looking up, but yeah. I mean, if I say that the ring, I mean, all Einstein really did was make an equation about what he saw sort of first light, sort of like first glance, he just sees a sun with a ring around it, and you say that ring is around the sun in its superposition in space. But you make an equation out of that, and the equation turns into that it needs essentially essentially a vector. Okay, it's just a vector, right? So it has a vector coming right to you, but it also has a vector behind itself because if you're looking at it two-dimensionally, you're looking up at the sky, the ring's right there and the sun's right there. You're looking at the blue sky, but that's obviously not where uh, the sun is. The sun is much further out, but the ring is clearly a reflection in the clouds. So, yeah, I don't really see what the problem is with that either. So, yeah, physics is becoming a suicide mission. Physics physics has just become like a suicide mission, like a brawl. I don't really know. I don't really know how to think of that any differently. I mean, I did think that I did think that I did think that what am I trying to say? The perturbation in gold, that was a little bit tricky. I mean, that was a little bit cool, interesting that you have a perturbation and a perturbation. What? I don't know. I don't remember now. That's unfortunate. Oh, we're talking about magnetic energy, so plus and a minus, and so these rotational or centrifugal bits are just I don't remember what it was called, but you have like it's supposed to be in a magnet. Essentially, what's in the magnet is something rotating one way and rotating a different direction. And I mean that's good to work with. But when so you're looking at the magnetic lines of force in the Wheeler experiment, and it turns into plus and minus. And yeah, it's but then you just look down at the center of one of the holes of gravity, and one of those holes of gravity is not really giving you any potentiality to nothing. It's I mean it's not giving you potentiality to anything. It's just a because you I mean it's just so close to the other degree of it's just so close to the other degree in the experiment, the positive, uh, that it's just going to be pulling the force in, so you can't get a true understanding of how the galaxy would be would be doing what it's doing. Whereas, like we would just think as I would just think of our galaxies as um, just in a constant sort of state of degradation. I don't know, like it just seems like like a asteroid could fly, like a asteroid could fly into the Milky Way galaxy and just join the Milky Way galaxy. I mean, that's what happens. Um, but there's just so much matter. Yeah, and then there's mass. Okay, and then these are some questions. I was going to answer other questions, but mass does mass equal quantity of matter? Does mass equal quantity of matter? Um, all right. Oh, shit. I wasn't feeling it earlier, and yeah, I just wasn't feeling it earlier. I know what was I saying? I know the quality is pretty not so great, but yeah, that was me just trying to review everything, and yeah, I'll try to do the questions. Mass equals quantity of matter. I think I was trying to get into it, but I didn't quite get through enough. I might do debate fit. Well, I might try to just go through the line of debate physics or something. If this goes all right, I didn't know if redundancy would help me or not. It probably will. So, does mass equal quantity of matter? You can imagine that there might always be two answers at least. If you just have a flat plane, if you just have a flat plane, there can be this idea like a distance squared that your a distance squared is basically work like a the inverse square root uh, equals negative inverse square root, and So there's a lot of equations like that. I think those are both Newton's or Cartesian, and yeah, those are pretty simple to understand. There's not really a there's not like a you don't need a lever to be able to do any of that stuff. So um, yeah, just it definitely. Well, I mean, yeah, what I was saying is mass. Is mass equal to quantity of matter or not? I mean, does it equal the force or does it equal the quantum bits? That's all you're basically asking yourself. You just go to the double slit, and the double slit usually gives you that answer. Um, the double slit gives you the answer. One answer is that they're all reflections. The other answer is that yes, there is magnetism between negative and plus or minus bits, and those plus or minus bits are what are able to control or shift the bits of matter in the photons. And just for the record, I think the best argument for photons, do they have bits or not? They're like, I mean, if you want to use the full force of energy and you're talking about a photon moving through bits, then yes, like the bits are moving very slowly, and the photon is a collection of those particles. And then we just go to cold fusion. So yeah, does mass? Yeah, what? Yeah, I already mentioned. I already mentioned the reflection. Uh, so does mass equal gravity? Um, right. So then you get this new equation again, or sorry, you get the same equation. You just get Newtonian force, or I mean, sorry, you just get force or energy. Essentially, a force could be momentum, like in a certain direction, and then something moving in that direction um, could put like there could be another push with the force. I mean, I don't really want to get too in depth into that. It's pretty basic to understand. If you have a line, the line can either be pushed towards it or gravity can pull it in. I mean, that's relativity, but yeah, force would be just something as pushing forward or even in drag that the bits behind the bits that follow the mass are pushing in a sense, which is well, not only that, but like they could be replacing as well, like moving at solar speeds. So does mass equal speed? Mass does mass equals speed, like you could say in momentum going through an electrical circuit. Then yes, if there is more uh, sorry, if the electrical circuit has more speed, then it uses more bits. Now it is really probably the mistake I made yesterday that the bits should not equal like kinetic energy shouldn't be all that necessarily right. Because yeah, you just imagine that there's more force moving through the sorry, there's more force. Well, I mean, yeah, I just basically said that you're moving the engine faster, so there's more force, or there's more momentum. Sorry, moving through the electrical matter. Like there's a direct current instead of the alternating current in the car engine. So when you use the direct current, that's when you would just say that there is more magnetism. There's a higher frequency, um, and that means that there'd have to be more bits. But that doesn't really that those things don't fall in line. There's a paradox there because there can't be interdimensional space or uh, free space. So mass mass multiplied by constant equals gravity or speed. Okay, so does the mass multiplied by the constant equal gravity or speed? I should have said there is another way to do it. Well, that would obviously be momentum. The other way to have more bits in the other way to see it is you don't need more bits because since you have a higher frequency, but you still have less bits, then just to get more bits, you'd have to say that you need more momentum. So, and that's obviously going to be force because you can't use energy in that equation because energy is going to corrupt the kinetic energy. Well, essentially the one half mass velocity squared equation because the one half mass velocity squared equation is just the complete paradox or like the paradigm for like potentials, right? So yeah. So mass constant equals g or mass constant equals gravity or speed. So again, it's going to be it's either going to be force or energy. If you're using mass multiplied by a constant, like say uh, like a ball flying through the air, multiplied by a constant. The constant can be the ground. The constant can be the air, and the ball will get pulled down. That's essentially how I would see it. And speed is sorry, speed. Okay, and if you have a mass multiplied by a constant, you could say in a quantum theory, if you have a bit, if you have a bit of energy multiplying a constant, um, such as a field, so you're doing a fourth dimensional. Um, like how does it equal speed? Well, it'll equal speed like almost in uh, conjuncture with photoelectric effect or something like that. I mean, there's no other way to put it. I mean, obviously in force you're using joules, newtons, and things. But I don't go there. But yeah, and then you just use the time. Sorry, the time. I don't know. What am I saying? Mass constant equals gravity or speed. Okay, speed. So yeah, and this. I'm sorry. The speed can be picked up by the field. Okay, so the speed will either be picked up by the field or it'll be brought down by gravity or it'll be brought down. Uh, they don't do air, so they weren't doing air back then, so they don't talk about molecules. And then there was the ether. Then there was the ether. So and then all right, does velocity equal weight? Okay, and this was what we were kind of talk. Well, this was what everybody was talking about how there can be a velocity in one direction, and that velocity there can be a velocity in one direction, and that velocity can press against the scale, and that scale, sorry, there's a velocity in one direction, and there's a velocity in one direction, and that velocity presses against a scale, so sort of a constant uh, scale. Now, I say that scale, um, if the scale is keeping something at a uh, constant rate, like a constant speed, then the velocity has to be infinite. It seems like it does, even though infinite isn't a good word. That's just because it's describing the speed at a certain point in time. So the speed can either slow down, the velocity can slow down, but at its uh, super velocity, then it'll equal um, however fast it is going against the scale. So I mean that's a good way to look at it. It's just with a lot of things like there's a scale like in all these things. So um, yeah, there's the velocity equals so yeah velocity equals weight. And then yeah, so it just be stops or slows down. So and watch more videos.